Hello, in this video we're going to see a basic example of programming the AVR microcontroller in assembly language. We are going to use this document as a reference, the AVR bare repository, which is basically a document that tells how AVR programming works and uses the standard tools in the GNU toolchain to do the programming. So in this first example, we are not going to use any integrated environment or anything, okay? So in this document, you have the general introduction about what you need to program the AVR, the description of the toolchain, so it's a very recommended reading. And at the end, you have links to the most important documentation on the AVR microcontroller. It uses actually includes some examples that can be programmed in an Arduino Uno board, which includes the ATmega 3 to 8P microcontroller. So practical examples are done in this board, but all the content is quite general for any AVR chip. Okay, so we'll start with our problem. Our problem is that we want to write a very simple program that reads 1 bit in one of the input ports in the AVR in the bit 7 in port D, and we read the value of that port, and we will copy that value to bit 5 in port B. Okay, so the good thing about that is that port B in the Arduino Uno board is connected to the digital output number 13 here. So, and this output number 13 is in turn connected to one integrated LED in the board. So if we have the board, we can test this program very easily. So our input will be this bit here, PD7. If we set it to 1, it should set the output to 1. If we set it to 0, we will set the output to 0. So it's not useful really, but it checks that we know how to use the digital input and output ports. Okay, and how do those ports work? So basically, the digital input-output ports in the AVR microcontrollers, they have 3 registers. One register, the DDR, is used to select if the bit is going to be an input bit or an output bit. And all this is for the B port, but we also have the C port and the D port. So we want to, in the case of the D port, we want to program the bit 7 as input, and in the B port we want to program bit 5 as output. Okay, so when a port is programmed as an output port, we write the value we want to output in the port B register. Okay, so it determines the direction of the bit, determines the value of the output when we use it as an output port, and if we configure the port as an input port, then we have the pin register, which is used to read the external value. Okay, we can program in the bits individually, so we can set some bits as output bits, some bits as input bits. So having said that, we can start our program. So for programming, first thing we need is to know what are the instructions. So I suppose that you are studying how to program the AVR microcontroller, and you have all the reference documents at the end here. Okay, so the most important documents are in this case, our board has the ATmega 3 to 8P chip. So this is a link to the datasheet. this is very technical with all the details about input-output ports and everything, including the instruction set. If you want to know more details about the instruction set, you can go to this link, which is the detailed instruction of that. And also you have the overall product page from the vendor of the chips, which is Microchip actually. And then here you have links to these documents and many other things and details, okay, like sample programs and everything. But for this simple example, we don't really need that lot of information. We can do it just with the instruction set and some knowledge of how the input and output ports actually work. So I have a summary of the instruction set here, taken from the datasheet. It's at the end of the datasheet somewhere. So just a reference to see which instructions we can use. We will not go into the details, but only we will use the instructions because I guess that you have already some knowledge about what the instructions are available. So for programming, the basic thing is, yes, you write your code in assembly in this case, then you need an assembler to assemble the code and everything. So we'll start by opening a terminal or just creating a document, okay? So let's create a folder. AVR examples, example. Okay, and inside here, you have to see that one project, one exercise should be in its own folder. Okay, so it will be example 1, and go for it. And here we can start programming. So we create a new file there. We are going to use the regular editor, the text editor in this Linux installation. And here I'm going to save the file here in documents, example 1. And the main file in any project is used to be called, yes, main, okay? So we are going to program to write the program in assembly, but we are going to use the GNU toolchain for the AVR family, okay? The GNU toolchain is the one that is used in most projects that use the AVR. It's the one used by the Arduino project itself. And with this set of tools, we can program in assembly, in C code, in C language, in C++, and this is the most general purpose tool set or toolchain we can use. So in assembly, we use main.s with the uppercase S. The uppercase is important because it means that when I give my file to the tools will run the C preprocessor first on the tool, so it can make substitutions of constants, which is important, okay? So any AVR project should start with a line like this, okay? Or should start maybe with some comments, okay? Simple program, assembly program. And with this include here mean that we are going to include this file. This will be done by the preprocessor because this is the sharp sign here, the C preprocessor, but that is used here as well. And because this file is the file that defines the names for all the peripherals that are used in the microcontroller. Okay, so that way, when we want to access the registers in the microcontroller, every register have an address in memory and also have an address in the input-output bus. But with these definitions, we can access the register by using symbolic names like this one here, port B or DDRB, PNB, etc. So we don't need to remember the addresses of the many registers we have. And the preprocessor also defines some preprocessor functions that will simplify our programming. Okay. Now we start our program in because our assembly code is going to be handled by the GNU toolchain. The front end to the GNU toolchain is the GCC, okay, the GNU compiler. The GNU compiler can compile C code, can compile C++ code, and can also assemble assembly language. So it's very convenient. The C compiler expects to find that the main program starts as a function that is called main. This is a function in C code or is simply a label in our program memory. Okay, so we start our assembly by saying we are writing in the program memory. This is the .text, so we are in the program segment. In the AVR means this is the program we want in the flash memory, in the program memory. Now the main label determines where my program starts. This label have to be global for the compiler to recognize it, so we use this one. All these dot instructions are assembler functions. Okay, it tells data to the assembler. It's not assembly code itself, but it tells the assembler what we want to do. We want this to be assembled, this because this is the text segment. We want this label to be global, and so on. Okay, now we start our program, and normally in every program we want to do some setup. Ports. For example, in our case, we want or we need to determine if our ports are going to be input ports or output ports. So let's go back here. In our case, we want, this is for port B, okay, but in port D we want to read data from port D7. Okay, so the DDRD register bit number 7 should be kept at 0. Okay, at value of 0. Normally ports are at that value, but in order to make sure we'll be forcing that bit to be 0. And in port B we want the data register B bit 5 to be 1. Okay, so where are those registers? Those registers are mapped into memory, so we can use regular memory instructions. Okay, I'm going to use them. If I don't remember the details, I can always go to my instruction set summary here, but I will try to do it. So basically, we can use regular load and store instructions. It means we can load in one register the DDRD, the value of the data direction register. Okay, now we can make sure that we set the bit number 7 to 0. Okay, we can do that doing an AND operation. So imagine if we AND the value of this register with this value here in binary 0 1 1 1 1 1 1. Okay, if we make the AND operation with this value here, what we get, okay, is that we will force the 7th bit to be 0, to be an input. Okay, and we will leave the other bits the same. So if we want to set a bit in a port, we can load the port in register and do this thing. Okay, we can do an AND with an immediate value. So we could do something like this and write the number in. We can write this number in hexadecimal because this is 7F if we want to use hexadecimal like that, or we can just write it in binary if we find it easier. I don't really know if I'm missing something, but I think it's fine. So once we have modified the value of the register, we have to store that value back on the register. Okay, we cannot operate directly on memory addresses. Actually, this DDRD is a memory address. That memory address is for DDRD's memory address, a 2A in hexadecimal, but we can use the symbolic name, so it's much easier like that. So we had set up the port as input. We do the same with the other port with DDRB. In this case, we want bit number 5 to be 1. Okay, so instead of an AND, I will use an OR operation, and we will force bit number 7, 6 will be the same because we are doing an OR, and bit 5 will be 1, will be an output, and all the rest of the bits will be kept the same. Okay, so this combination of load, store, and logic operations can be used to set any bits to 1 or 0. Okay, we are just setting one of the bits, but we may select to define any bit as input or any bit as output, or we can just load a we can just in this case we have read the register first because we only want to change one of the bits. Okay, but we may have done it in a more direct way. For example, we may have simply done something like a load R16 with the value we want for with number 0, for example. Okay, and then we may have store DDRD with R16. This could be load immediate here, and this will have set all the bits in the port D as inputs. Okay, but in this case we have done it in a more general way. We have done it so that we read the old value, we set only the bits we want to change, and then we store back the value. Okay, this is more general. Actually, we leave the other bits we are not using unchanged, which is good practice there. So all we have to do here is to store DDRB with the value we have just changed. Okay, so this is the setup. Now we will enter the main loop. In our main loop, we basically check the value of the input. The input is in, because it is set as an input, the input is in pin D, in pin D7, okay, and the output is port B5. Okay, so we will enter a loop here. Probably our loop label will be over there, and we are going to read port D, check if it's the bit is set or not, okay, and then set or not the output. Let's load it first on R16 again. The input is pin D, okay. Because we want to check one of the bits, we are going to do an AND bit, and then with an immediate value of R16. So we are doing an AND operation with the bit we want to check. It will be something like this, with 0B1 So in this case, when look, if P and D is the input is set, this is 1, the other bits I don't care, okay, and I add the value to this one, basically the result is that if the result will be 0 for all the bits, and it will be 1 if the 7th bit is 1, and it will be 0 otherwise, okay? So by doing this, we obtain a result that is 0 if the 7th bit is 0, and a result that is different from 0 if the 7th bit is set. So basically, we end it, and now we can check. We can use a branch instruction, okay? Now, if we can branch if equal means that the result is 0, or we can branch if not equal, depends what we want to do, okay? So we can, let's say, if we will branch if equal, being equal means that the result is 0, so we will jump to a new label. Is 0, okay? Elsewhere, we will solve it here, okay? And here we will write whatever is necessary, okay, to handle the case when it's 0. And if we don't branch, here we have to do whatever we want to do when it's not 0. And when it's not 0, what we want to do is to set bit 5 in port B equal to 1, okay? So we can read port B, set the bit to 1, and store back port B. So the best thing we can do is that at the beginning of the loop, we can read the port B here, and then we set and we store at the end, okay? No matter what happens, okay? So we read the port B here, we decide what it's going to be the value for port B, and then we store the final value here. So it also reflects how programs are really written. Normally, programs are not written starting at the first line and ending at the last line. You write your code as you see the algorithm in your brain, okay? And then you add the details later. That's why I'm doing the exercise again, because it's very important to see the order in which the lines in the code are written, okay? So we will load in another register a value of the output port B, okay? Read port B and save for later. You can write a comment whenever you think you are not going to remember why you did it in that order. Evident things don't need comments, okay? That enough explained in the code. So if it's 0, what I want to do is that we have R17 is our former value in port B. So now we want to set it to 1. So we will do is that we will OR R17 with a binary value that will set the 5th bit to 1, okay? So we use OR when we want to force bits to 1. We use AND when we want to force bits to 0. That's the idea. Okay, that will do the job. And now this is in case it's not 0. I don't want to execute that, so I will jump to another label, which is continue the normal program, okay? Great. So now, if not 0, so if it's not 0, I do this thing, and then jump and continue my program here. But if it's 0, I want to set the value to 0. So I will use the AND on R17, and we make sure that the fifth bit is set to 0. Okay, now we just continue my program. So the label, continue label, should be here, and all I have to do now is that I have read the value port B, I have selected which is the new value, so I store the value back to port B with the updated value in register 17, and we just repeat it again. So we have checked just once, we want to do it all the time, so as soon as the input changes, we can go and repeat it. Okay, so that's it. Basically, this is our program. We save the program code, this is text code with our program. Now, some details, for example, we also have the jump instruction, okay, that will jump to a label, but we have the relative version, the R jump instruction. The relative version cannot jump that far. It can only jump around the place you put the instruction, a few memory addresses before and a few memory addresses after. Okay, so you cannot jump anywhere in your program if your program is very big, but your air jump instruction takes less space and executes faster. This is something you can check here in the instruction summary. If we go to the branch instructions, we have the relative jump. The size of the instruction is not here, but believe me, it's shorter than the regular jump. I think it's shorter. Okay, I'm not really sure now, but we may check in the document I mentioned before with the detailed description of the instructions if you have interest. But the relative jump will be executed in 2 cycles, okay, in 2 clock cycles, while the regular jump, which is below here, is somewhere here. Yes, the regular jump here will be executed in 3 clock cycles. So the relative jump is faster. It is faster because it uses a smaller number. And I think the regular jump, the instruction is bigger because it needs another position in program memory to store the address where it have to jump, because the instruction code is 16 bits, but the addresses are also 16 bits. So it needs to, after reading the instruction, it needs to read the address from program memory. So it takes 1 more clock cycle. While the relative jump, the number is smaller and it is included with the instruction. Okay, so the idea is whenever you can use a relative jump, use a relative jump and not the regular jump. Okay, so we save our program. Now we have to do the things. Now the next step would be use an assembler to convert my assembly language program in a compiled program. Okay, once we have that, we could upload it to the board and check if it works. So in our repository here, if we go back, we have all the instructions to do that. So after the initial description, it has a very practical guide, very short guide to the commands that are needed to complete the process. Okay, so this is the commands that normally the tools execute for us. Okay, but in this case we want to execute them ourselves just to see how it works. So we will open a terminal where our project is, and we want to assemble that program. Okay, it can be done with the GNU compiler, the C code compiler, because the GNU compiler actually works as a front end. So if you give it a C file with a C program, it will compile it. If you give it an assembly program, it will just assemble the program, okay? And the thing that the compiler needs, it needs to know what's the type of microcontroller you want to generate code for, because different chips have slightly different options, okay? So we basically execute that, and the AVR version is the AVR GCC that we already have installed, and we use those options, okay? MMCU just to is equal to the 80 mega 328p, and we are going to my compile and assemble program will be in that file main.elf, and the source code is in that file, okay? Complex programs may include many source code files. The compiler will handle everything for you. Now, the option is that if we want to debug our program, we may include the -G option. It will include, together with the executable program, it will include the places of these labels in the source code. So it will include information that links the compiled code to the source code, so we can later debug the program. So it will simply, we run it, and okay, we have some errors here that we have to check. It's completely normal, okay? Because it's normal that we make mistakes. So I already know what's my mistake, because it says in line number 10 that we require a pointer register. This is because I've used the wrong instruction. LD is the instruction for loading with a register in the middle, using register and indirect addressing, okay? If we want to load straight from memory, we need the LDS instruction, and here as well, okay? So this is my fault. And so I will change all these instructions. All these instructions should be a straight addressing mode, okay? So we save our program again, we try to assemble it again. Okay, and that's it. We've been lucky, it's assembled. Now, if we want to test the program, actually, once you have the tools installed, it is very easy to check. And okay, one question is, how do we install the tools? In this document, you have the options. I'm using a Ubuntu Linux distribution here. So if you want to install the tools, you can simply execute this command here, okay? We institute the apt with the tool manager, the installer for Ubuntu, and everything is included by default in the Ubuntu distribution. So installing these packages here will give you the complete tool chain to program and to upload code to the AVR. In a different platform, like in Windows, there's the toolset is also available. Probably the best option in Windows is to install the Arduino integrated development environment, because it's, if you are going to use an Arduino board like this, you probably have it installed, and the Arduino software includes the toolchain. So you may install that and then configure Windows so that it looks for commands where the Arduino software installs the toolchain. Okay, you have to find that yourself, and there are other options. Okay, but I'm not very familiar because I don't use that operating system often. So you need to have the tool set the toolchain available anywhere. Once it's done, everything is pretty much the same. You edit your code and then you write the comments to compile and do that. So we can try to go here and we can try to program it directly. Okay, if we want to upload the code to the microcontroller, we need these couple of comments you have here. Normally, programming software, when I mean programming here, I mean the program that upload the code to the microcontroller, they use an hexadecimal format for the code, not the regular ELF format, which is the format actually executed by the processor. Okay, so our programmer, which is the AVR Dude program, actually supports ELF format, so it can be used with that, but it is more general to use hexadecimal format. So it is simply, we are going to copy this command here, which basically says that we want to translate the text section and the data section, if any, in our program to this is the Intel hexadecimal format. Okay, and that's it. Okay, we put the input file, which is our compiled program, and the output file. Okay, now we have the code compiled here. We have the code in hexadecimal format. It's a regular text file with a hexadecimal representation of our program, and this one we can upload. Okay, so I have a board already connected to the computer, so you can see it here, and this is connected with the USB cable. This is the other thing that is good about using Arduino boards for that, because they already have a bootloader inside and it's very easy to program. Okay, we don't need an external board or anything to program them. So to program it, we need to execute the programming software and give several instructions. For example, this means we want to program using the Arduino interface. We want to program through the Arduino bootloader. It supports many other types of programming. If we use a different method, we have to find out what to put here. This is the chip we are programming, the one found in the board. This is the serial port where the board is connected. Okay, in Linux, serial ports that convert from the USB are like this typically: TTI, ACM0, ACM1, and so on. I only have one board like this connected, so most probably is this port here. If not, I will change that. In Windows system, the serial ports are normally called COM1, COM2, and so on. This is the baud rate, the speed at which we are going to connect. This is pretty standard. And these options mean that I don't want to erase the memory in the microcontroller first, and that I want to do a memory operation. I want to program the flash. I want to write it with this file here, okay, which is in hexadecimal format. So it's lots of information is condensed here. Fortunately, if you already know the command as you have here, we can just copy the command to our terminal. And now you have to pay attention to the board, because these LEDs here will flash when we are programming. Okay, so you must take a look there. Oh, it's not working. So let's see what happens here. Oh yes, I know. The problem is that I'm recording this video in a virtual machine. Okay, so it's not really connected to my virtual machine, but to my real machine. So I will just tell my virtual machine that I want to connect the board there. Okay, and it should be connected now. We can check with the dmesh program, which gives information about the operating system kernel. Okay, so we try to find out. Okay, this is the last message. Once I have connected the board to my machine, I have done it virtually, but it is the same. It have detected the new device. Okay, if you see, it have assigned the TTI ACM0 device for this board as was configured here as I expected. Okay, so now it should be right, so I can try the command again. I go up. This is the same program as I've done before. So take a look at the board, look at the LEDs over there, and we see programming works. Okay, it seems it's been done okay. And now it should be working. Okay, Okay, so here we have our input is actually pin 7 here, not pin 6. So I will connect a cable to pin number 7. This is port D7. Okay, and look at the LED here. Okay, it's now when I connect it to 0, I can use the ground pin here. It works. Okay, we have a 0 here, and then it reads this 0 and sets the pin number 13 here to 0. The LED turns off. If I change it to 5 volts, which is we can take from here, then the LED is connected. Okay, what happens if I do not connect the cable? Okay, if you don't connect the cable, it's not a good idea, because who knows what it is reading. Okay, it may read a 0, it may read a 1. If I connect it to 0 and then we disconnect, if you see it, even if I touch the cable, the value may change. Okay, because here it's in high impedance, it's left to the air, so depending on the electrostatic thing, it can change to one value to another. So we have to connect it to 0 or 5 all the time, okay, to avoid a wrong behavior. But one thing that we can do with the Arduino boards is that we can connect it. We can configure it with a pull-up. We can tell the board to connect a resistor internally in the chip, so that when the cable is not connected, it will be slightly connected to 5 volts, to the high voltage. So it's never left there. It's very useful, because in that way, if we want a 0, we connect to a ground, and if we want a 1, we just disconnect. And this is very good, because if we want to drive this line with a push button, we can use a push button, and we don't have to add our own pull-up resistor. Okay, so we will add that to our code. The pull-up resistor is configured by, in the input port DDRD, when it works as an input, the port D register determines if we activate the pull-up resistors or not. So I'm going to load a value in R16, and LD R16 we are going to load this one with a 1 here. Okay, this is the value we want to program in port D, 1 at the 7th bit. Once it's loaded there, it will activate the pull-up. So we stored stride to DDR, this could be port D, R16, okay? Activates PD7 pull-up, okay? Okay, let's save it. Now we can, repeating everything is really fast, because we have the comments in our terminal. Our terminal will remember the comments. So we will compile it again, no errors. We convert it to hexadecimal format, no errors, and we program again. Look at the flashing like this there. Okay, that's it. If you see, it's not connected, but it's stable now, okay? Because we have our pull-up resistor working. To set it to 0, we just have to connect it to ground, okay? Okay, so this is all for our first video introduction to programming. We'll see some more details in the following video. Thank you.